So this is a bit different video this time. I'm going to interview someone about battery technology. So what's your name, by the way?
I am Fabienne Gschwind.
Okay. And you work at
Helmholtz Institute Ulm.
Okay.
It's a new electrochemical storage institute, as an institute which basically investigates batteries.
Okay.
It's located in Ulm, so between Munich and Stuttgart.
All right. So so you what is it that you are investigating in?
So we have, the institute is quite big. We have parts doing the normal lithium battery investigating or calculation, simulation.
Okay.
And we have a tiny part or a small part which does novel battery chemistry. So new development in the battery field.
Okay.
And for instance, you have the common lithium oxygen and lithium sulfur. You have the new magnesium battery.
Okay.
You have the sodium battery, chloride batteries, and it's like me, a few researchers doing completely new system. It's fluoride ion batteries.
Fluoride. So is
fluoride is that what you have in the toothpaste, so the
okay, yeah.
F minus,
yeah.
And it will be the opposite, electrochemical opposite of lithium.
All right. Well, I'm not an expert on batteries and all that, so you have to explain the basics.
So basically you have lithium which you have in all your device.
Okay.
What it's doing, lithium is an element which wants to get rid of its electron to have a better stability.
Okay.
It's the octet principle, maybe you have it learned in school. And it wants to get rid of it, so it delivers this electron to the electric circuit. And it will be so oxidized to lithium plus and travels through the electrolyte to the anode and so on. And it's basically this process that the lithium gives up one electron. And fluoride will be the opposite. Fluoride wants to have, or fluor wants to have one electron more to get this shell complete, to be more stable. So he will take from any other element on fluor to get F minus, so fluorine minus, a negative element which has too much electron, travels through the electrolyte and go to the anode, or which system we have. So it's the opposite working principle.
All right.
So it's completely new.
Yes, but how far is your
we are very basic. We are at maybe where lithium battery were 50 years ago. So we just did the principle proof to show it theoretically it can work. That's where we are.
Also, so you have like a working prototype or something?
We are currently, one of my master students will build one working prototype. I am working on this little Zweglok cell, which are holding just a few milligrams of material. And with that, I can in the moment deliver one nice discharge at room temperature.
Okay.
Because the problem with fluoride, it was known since several years for solid state. So that means high temperature, like 100 to 200 degrees.
Celsius?
Celsius, where you could work the battery. And my job is to develop it now for room temperature.
Also before you had to actually heat it up?
Yeah, you have to heat it up. That's the fluoride which is bound in the structure. The crystal can move, so you need to heat it. And I am on the part which works on the room temperature one, where we have a liquid, let's say electrolyte, where the fluoride is traveling.
So now,
difficult.
Now it works. So it works with room temperature now, and eventually it can work even in sub-zero temperature. I see. Oh, well, that's cool. But I mean, you said that it's 50 years behind lithium technology. So, but then again, in the early days, 50 years ago, what did people say about lithium batteries?
I think one of the first papers, they were basically laughing at him, like, come on, we want to use this lithium in your pocket, it's much too dangerous.
And now we have it like...
Everybody has it.
In the phone and in everything.
In your car, in laptops, everywhere. So it's big progress out of it.
Yes. But this new battery technology, I mean, what kind of potential, what kind of advantages does it have over lithium?
Yeah, of course you have this not very commercial argument, just doing new research and investigating. You never know what will open, what you will discover. Okay, that's not very good to get money for that. The other one is with theoretical calculation, we can show that fluoride battery will be superior to the common lithium battery.
Really?
Lithium is gravimetric, so per kilogram. Lithium is quite good.
Okay.
But when you look per lithium,
okay,
it's not so
volume
much.
Wise, yeah?
Yeah, the volume, lithium is not so good. And there the fluoride will be much better. Maybe double or triple even. So the capacity on energy density than what is actually on the market.
Also, basically, let's say the Tesla battery, it weighs 600 kilos. I've seen it. It's almost like this table, actually larger than this table. Yeah. So you would still have a 600
kilo, but it could provide more energy density.
But it will be capacity. Much smaller.
Yeah, it will be the same size, will provide more energy, or for the same energy, it will be smaller, or heavier.
So you would have a 600 kilo battery, but it's 1/3 or half the size, is it?
You can so per kilogram you can have more. Per liter, so per volume you can have more.
But if you have the same size, then it would weigh like 1,200 kilos or 1,000.
Yeah, that's depending. The battery. In it, the battery material, you have not so much, you have a lot of casing and metal and wire cabling. So that's all this battery design behind.
So I see it. So the way I understand it is that you can make a 600 kilo battery, but it's much smaller, so you have more space.
Yeah, it will provide the same energy, but in a smaller volume.
So that's
that you can
in terms of Tesla, for instance, a car. Because that's a problem with electric cars nowadays, that battery takes up space.
Yeah, sure.
And it will free up space in mobile phones.
It will be smaller and a bit heavier maybe, but smaller.
But people don't care if it weighs 50 grams extra. Yeah. If you can, you have standby time, or, I don't know, 1 week or something.
Yeah, sure.
So that's cool. So it has some potential. And what about, the lithium batteries? They have, the skeptics, people who are anti electric car, they always complain that lithium batteries are bad because they have to be manufactured in China or somewhere. Yeah,
the lithium metal or the metal in the batteries, for instance.
But how does that work?
So fluoride will be interesting because we have in Europe, let's say in Europe or Germany, whatever, there are quite a lot of fluoride compound in the ground, like calcium fluoride, fluorite. It's a mineral which is very common around us. And also in seawater you could find it. So it would be, if we do a careful design, we could be able to build here in let's say Middle Europe or Europe our own battery factory which use element which are here, so just kind of home sourced battery.
But can they also be made in America?
Yeah, there will be also the elements there.
So
it's quite common, widespread. For example, calcium fluoride. Of course, you need to treat it a bit further then to get.
But unlike lithium, where you mentioned
Chile has this big salt lake where they get the lithium chloride, and there are a few other mines around, like China, maybe even Kazakhstan. So I would have to check that, but not here in Europe. We don't have so much of it. You can extract it from the seawater, but that's costly.
So basically, all the iPhones and the laptops and whatever that are used in Europe, the batteries come from China or Chile?
The material inside. Okay, the material inside. I'm not sure where the battery is manufactured. There are, of course, also manufacturing in North America where they build it together. But somewhere the element inside needs to be extracted from the ground.
Yeah, so it's better.
Yeah, it will be an alternative in case of never know what's happening. Sometime maybe we will need to have battery which we can make ourselves here, using material we have here. Then it would be an advantage to have in case an alternative system.
Okay, yeah, because we never know. Yeah. You never know the materials, if you will be able to get them there. Or not. I mean, the supply might stop one day.
Yeah, you never know. It will be also more sustainable if we don't need to ship so far all the material and we can have it here. Yeah. It will get more jobs here when we start ourselves.
But
it's a possibility we can offer.
But okay, so but it's still in the beginning.
Yeah.
But you know much about it. You know a lot more than me. I'm just a driver out there. But so it has some potential to become maybe an alternative to lithium.
Yeah, why not? I'm a bit dreaming, of course. What we could do in the moment, I am just in the very early stage, so I can have one discharge. But let's assume we can have a very cheap battery because we have all elements around. We can build it from like old piece of copper as anode. We can use calcium fluoride or whatever. We could have one battery which delivers the same amount of energy like a standard one. With maybe even it has one discharge. Why not? When it's so cheap, you just drive with a car in the gasoline station, and instead of waiting that it's full, you just put a new one in it, and you go on.
But it's not.
But then it can be manufactured. It's so cheap, maybe.
Like one-time battery.
One-time battery, yeah, maybe. Or then you can do it somewhere else, or recharge it somewhere else, so it will be much faster than to wait on.
Yeah, but people will probably want a rechargeable battery.
Yeah, sure, but you could do both. Why not? Why not? It's just a possibility.
But what about the recharging time? And because with the current lithium technology, there are many concerns. You have recharging time and also lifetime degradation, and also about the problem with temperature. What else? Yeah, so, you know the lithium disadvantages.
A bit, yeah.
So, I mean, will is it too early now to say?
Yeah, I am not there. Because I'm basically alone on that research with some students around, and I'm working on the complete battery system: the anodes, the cathodes, the electrolyte, all the problem, all the mechanistic. We don't know how exactly it's works. We still have lots of understanding to do. But maybe at a certain moment, maybe even a few months, I go back in the lab after tomorrow, and I will start again to do new research on the anode, and maybe I come up with a good idea, or one of my students come up with an idea, and suddenly, we have no possibility to charge it, maybe. No. You never know how fast it goes.
Yeah.
So it's possible.
Yeah. Well, sounds interesting. Maybe we should do another interview in like 6 months or 1 year to see.
I can tell you what's happening.
Yeah.
It's not if we do the research just right now, and maybe just not now, but maybe this afternoon before some of my students which work for me, maybe they already did some more interesting things.
Yeah.
Yeah, it's all everything we do is new, so you don't know where you go, and it's fun.
Yeah, but I think. There are some clips. You have some video clips, so maybe we can. I can
have
show
a look
you.
How we build it.
I can show you some of the clips after this video. So, but it's interesting. Yeah, I hope it will develop to become something maybe better than lithium.
Or maybe just an alternative.
So
it's good.
Yeah, maybe alternative. Like today, we also have some different, but there are also some types.
Sometimes you have advantage for one system and disadvantage, and when you have different systems, you can choose the best suited your application.
But nickel cadmium died. Yeah, because nickel metal.
Cadmium especially is very toxic.
Oh yeah. So some types kind of died off,
and you coming.
Maybe if there's a new type that has some of the. Maybe it doesn't have the disadvantage with the lithium. Like there are rare cases where the lithium can catch fire and stuff. Yeah. So that's also a concern for.
The flammability of the lithium.
Oh yeah. By the way, how is that with the fluoride?
Yeah, there are different. The most common way to explain it is this dendrite formation. Basically, you have metallic lithium forming like a spear, a metallic spear, which goes from the one electrode to the other and having a short circuit. And then you have a short circuit and the battery starts to burn. So that's the dendrite formation. It's one of these runaway case.
Well, can that happen to any battery?
I have to think. I think there are some which are more which can have it more like the polymer are more sensitive to that. In the institute where I am, we have like groups doing simulation and trying to understand exactly this working and how you can work around. And I know of other research groups where they try to do like protection jacket for the battery so it won't pierce. Oh. But of course you have also other process which can induce this flammability. But I'm not such an expert in battery, unfortunately. But there is also still research ongoing. Even the battery are very well known. There's still lots of people trying to understand it better to avoid this problem.
Well, this has been interesting. So I don't know, but maybe I'll keep in touch. Want to find out more how this.
And when you come next time to Germany, you can drop by.
Maybe in München. Well, there are some superchargers there, so
yeah. You can just drop by and do your tour through the building.
Yes.
Our institute.
Well, okay, but thank you for the interview.
Yes, thank you very much. Yeah. It's difficult to explain you such a complicated topic in a few words, but hope it's working.
Yes. Okay. Well, that's it then. So we'll see. Yeah.
Okay, so like promised, I want to show you how to build a little battery. We use this prototype Zwecklock cell, and so it's done. So here I have opened the cell, so I can nicely fill in the cathode and anode and everything. So here I have the cathode. In that case I use bismuth fluoride. It's my standard cathode material. So it's basically a little piece of metal, stainless steel, and we coated it with bismuth fluoride carbon powder. So down here, that's the first part. And as anode we have a little piece of magnesium. Normally I assemble it in the glove box, but here I have to take it out so it's easier for doing the moving. But we cannot do the magnesium right on the cathode, it will not work, so in between we add a separator, and that's basically a little piece of tissue like the paper we have here. So let's take maybe 2 little pieces. And now we need electrolyte to conduct the ionic charge. So I have here my fluoride conducting electrolyte. And normally you use a few drops, maybe like 10 drops or so, 1, 2, 3, 4, 5, 6, see? Yeah, it's nice and wet. So, and in the last step I take the little magnesium piece. Okay, it's not so easy. Maybe I do a second one. So we have enough material. So, and we add just a normal stainless steel collector, it's called, to collect the incoming electron. We could use directly the stamp, but so we don't we will not make it dirty, so it's easier to use a little piece of metal. And that's it basically, so we just close it. And we can press a tiny bit together, so. And very important, we note what we have done, because otherwise we don't know where is what. So bismuth fluoride and magnesium is here. Okay. Okay, we have here our battery, and now we want to know how it will perform. So we do it in a battery tester. I will just do it like back here. Here you can see I have my space here. So the magnesium is anode, so it's on the negative side. And now we can have a look what's happening when we test it. So here you see the computer software testing the battery. I know that it's a battery which is here, and it's about, the OCV is about 1.5 volt. And what we can do is we can set up a little program. So here we have different steps. In the first step I want to have so during half an hour just nothing will happen with the rest. And then I would like to have a discharge, and I tell the software to discharge to 0.1 volt with in that case 0.00001 ampere. And then it's charging, and the whole thing does a loop, so it starts all over again 10 times. Okay. So, and discard it. Start channel.